But when we look at where earthquakes occur on our planet, it's going to be right along our plate boundaries. We're going to see that most earthquakes on our planet happen along the circum-Pacific belt. And you might know this as the Ring of Fire. This is the area around the Pacific Plate where we have tons of those megathrust faults. Where the Pacific Plate is subducting underneath a continent, it's creating the megathrust fault that creates the largest, deadliest earthquakes and is also capable of creating those tsunamis. But we also get earthquakes in mountain building. So over here we see the Alpine Himalayan belt. This is where India is currently colliding with Eurasia and creating the Himalayan mountains. We have two continents colliding, forming a mountain range and creating lots of large destructive earthquakes. But we also see lots of transform earthquakes as well. Probably the most famous one is the San Andreas Fault here in California. This is the one that creates cyclical earthquakes. So we might go, let's say, 100 years without a massive earthquake, but it happens roughly every 100 years. And on our planet, we have tons and tons of really small, weak earthquakes. And these primarily happen along our divergent boundaries. Here at divergent boundaries, we have two plates that are separating away from each other. We still have earthquakes that occur here because we're moving two massive plates. It's going to create a lot of friction in the plates that are moving. So our divergent boundaries do create earthquakes. They're just not large destructive earthquakes. They're just very weak with very minor amounts of shaking. But we're going to see that certain areas have more earthquakes than others. We're probably all aware that California gets a lot of earthquakes, but here in Florida we get very few, if any. And that's just because earthquakes are a lot less frequent in the central and eastern United States. This doesn't mean that they never happen, it just means that they're not common. Whenever they do happen, they are actually more destructive than if we were to have an earthquake out west in California. And this is because the rocks underneath the central and eastern part of the U.S. are older, colder, and more rigid. This is going to allow those seismic waves to more easily move through the rocks and travel larger distances. We'll also see that because these rocks are rigid, they're going to be better at shaking than if they were softer rocks that would simply break. But the reason why we're having these earthquakes in areas that are not tectonically active is because these are intraplate earthquakes. They're happening away from plate boundaries, but for some reason stress is building up under the ground in that area. So this map is just showing us some earthquakes that have happened east of the Rocky Mountains in an area that is not tectonically active. So all of these are our intraplate earthquakes. They are not happening along a plate boundary. And as I said on the last slide, these aren't very frequent, but when they do happen, they can be very damaging. So for example, there was an earthquake in 1812 in Missouri, which is nowhere near a plate boundary, that produced up to a 7.7 magnitude scale, which is an incredibly large, very intense, and destructive type of earthquake. If we're trying to figure out exactly where an earthquake happened, we need to look at seismograms. And here we're going to use a process that's called triangulation. And here, tri and triangulation is important. We're going to need at least 3 seismograms, or 3 sets of data from this earthquake. And we already know that our waves are going to arrive in a very specific order, where it's our P wave first, our S wave second, and then our body waves last. But here we're looking at seismogram data from 3 different locations: New York, Alaska, and Mexico. And these are all recording data from the exact same earthquake. But you'll notice they look different from one another. They have different amplitudes or different heights of these different waves, But you'll also notice that the timing of the waves are different. We always see that P waves arrive before our S waves, because our P waves just travel faster than the S waves do, due to the fact that they move more like a slinky through push and pull than they do like a rope, like the S wave moves up and down. But we're going to see that depending on our distance from the earthquake, the difference in the arrival time between our P and our S waves is going to change. If we're really close in location to the earthquake, our P and S waves are going to arrive close to each other. But if we're really far away from the earthquake, like thousands of miles away, there's going to be a longer period of time between when the P and the S waves arrive. So when we're looking at these diagrams, here in seismogram C in Mexico, there is the shortest difference in time between P and S waves. So this seismogram was recorded closest to the earthquake. Here in Alaska, there's a larger difference between our P waves and our S waves, so this location is farther than the earthquake than Mexico is. So we can use the difference in arrival times between our primary and our secondary waves to determine exactly how far away we are from where the epicenter, the surface that's shaking the most, is. So there is some math involved, but there's also a really just quick and easy chart that we can use. If we're looking at a seismogram and there is a 5-minute time difference between when a P wave arrived and when an S wave arrived, we would be able to see at that 5-minute difference here along our time axis, if we came straight down to our distance axis, it would tell us that we are exactly 3,700 kilometers away. You do not need to know this chart, but just know that a chart exists so that we can convert the time difference, the arrival time difference between P and S waves, into how far away that seismogram is from the actual earthquake. And then once we know the distance that seismogram is from the earthquake, we can triangulate the earthquake. If we could draw a circle showing that distance all the way around in a 360-degree circle around the location that recorded the earthquake, we can see locations that potentially could have occurred. But if I only had one seismogram, the earthquake could have happened anywhere along this red circle. If I have two seismograms, now it would happen somewhere where those two circles intersect. So the earthquake could be here, or it could be here. The reason why we triangulate or use 3 is because when we find an area where all 3 circles intersect, that is the epicenter of the earthquake. That's the location on the surface where the ground will be shaking the most as it releases that energy.